Now the mode is worth bringing up, I guess, but it has very little serious application. I thought of an example of where the mode might actually describe something useful. Suppose that you wanted to know the average size shoe for men in this country. What's the average shoe size? Well, what would you do? You'd probably call a shoe manufacturer and say, well, look, what's the average shoe size you guys sell for men? And probably the executive up there would say, well, it's size 10 or whatever the number is. Would probably have it off the top of his head. Now, did he really go out and calculate the average shoe size? No. It's which one do they make the most of? And with very few, with a limited number of responses, there are not many different shoe sizes. Most men wear between 8 and, we'll say 13, I'm not sure, something like that. That covers probably more than 90% of the shoe market. With very few limited shoe sizes, the size they make the most of is probably pretty close to the average, very close to the average. Anyway, that would be the mode of the data. The mode is the number or numbers which appear most often. And so, and I said numbers. It's possible to have more than 2 modes. And anyway, and it's also possible to have no mode. If all the data you see, all the numbers are all different, there was no mode. So anyway, mode, that's what it is. I think it occasionally you see this in a distribution of data, and their mode is used to describe something different. For example, and I've never done this, I've never looked at it, but I'm kind of guessing. Suppose you measured the height of adults and plotted them out on a graph. What would it look like? The height of adults. Okay. Now, I'm guessing it might look like this. There are very few people that are very tall. There are very few people that are very short. Most people are clustered in the middle. But if it came out looking like that, what would explain it? Women and men, right? Men are normally taller than women. So you would have probably a cluster here that's primarily men and a cluster here that's primarily women. And this would be called a bimodal distribution. In other words, there are 2 modes in essence. Bimodal would be kind of an unusual type of distribution of data, but it does occur out there. And so anyway, that's a usage there. All right, now let's get on with the mean of the data. The most useful measurement of central tendency is the mean, because the mean or average is a computation that can be expressed in algebraic form, and so therefore it can be used in theorems, various theorems used in statistics. Okay, so I'm going to make up some data, just make up some numbers, and I'm going to keep this chart on the board to talk about the next topic, which is the measure of central tendency. All right, so let me finish erasing. Here's some numbers I made up, distribution of data, and there are 10 numbers: 5, 7, 5, 6, 3, 4, 5, 9, 6, and 4. Okay, so right away I have another summary statistic. The most basic is how many pieces of data are you working with? In this case there are 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so n equals to 10. So letter n is always used to denote the number of pieces of data that you have. Alright, so n equals to 10. Now, to find the average, I add all these up, don't I? So let's add them up. I have 5, let's see, 5, 12, 17, 20, 30, 35, 45, 54. So it comes out to be 54. And I'm going to call this sigma x. So I'm going to write that a little bit larger. Sigma x is 54. Alright, so what is sigma? This E-looking symbol. It's not an E. It's the Greek letter sigma. It's the uppercase sigma. And sigma is the traditional Greek letter in uppercase form to indicate a summation, an addition. And so my variable I called x, so the sum of the x's is 54. Now, what is the mean of this data? All right, well, I'm going to call it x bar. So the mean is x bar is 54 divided by 10. So the mean, x bar, is 5.4. Okay, so that's the center of the data as computed by the average. All right, extremely simple formula, and I see that I didn't write it out. What I meant to write here was sigma x over n is the formula for mean. Sum of the x's divided by n is the formula for mean, and in this case is 54 divided by 10, 5.4. All right, I'm going to use this sigma notation throughout the course whenever we need it. And so it's pretty easy to get used to. And it's kind of a nice way of writing a formula. So, all right, so that's the average of this data. Now, I want to talk about, and using the same data, I want to talk about a measure of dispersion. So let me do just a little bit of erasing here. And let's see, our n was 10. Sigma x was 54, and x bar was 5.4. All right. In a little while, I'll talk about x bar and other letters that we use. But the next issue is called the measure of dispersion. D-I-S-P-E-R-S-I-O-N. And to disperse means to spread or to scatter. So a measure of dispersion measures how scattered these numbers are. How far apart are they? And so we need to come up with some way to determine some kind of average spread of this data. So if the numbers were had a lot larger range, say they started at 3 and ran up to 50, we'd have a much broader range of numbers. We would have a wide dispersion. If the numbers are only like 3, 4, or 5, they'd be a very short, very tight dispersion. So the number we come up with is going to be large. In the case of, trying to get used to my camera here, I've remodeled this room, and I got the board on a different wall and the camera in a different place, so I'm kind of getting used to it again. Where was I? A wide dispersion is going to have a larger number associated with the data than a small dispersion. So anyway, and there are several ways to measure dispersion. One is called range. It's very simple. The range of this data goes from 3 to 9, so the range is 6, or from 3 to 9. Not very useful for statistical purposes. There's no formula there. So the other two are called the variance and the standard deviations. Standard deviation. Variance and standard deviation. Now the variance literally is the square of the standard deviation, which means the standard deviation is the square root of the variance. That's all there is to that. So, but books often talk about variance. I've never seen them use it other than as part of a calculation, so I'm really not going to worry about variance. I'm just going to go straight to standard deviation.